Good afternoon. I'm Arun Serafin, Deputy Director of the Emerging Technologies Institute at the National Defense Industrial Association. Thank you to all the attendees for your support of NDIA and ETI, and thank you for joining us for today's webinar, Digital Engineering 101, with Dr. Thomas McDermott. This webinar is part of our Tech 101 series, where we try to distill complex technologies into introductory webinars with a focus on their national security impacts. The highest level, digital engineering can be used anywhere product engineers want to make product development processes more agile and responsive to both market demands, customer needs, and technological opportunities, and speed the process of moving technologies from research and innovation stages into systems engineering and development and production stages. DoD, in trying to leverage these methodologies, announced its digital engineering strategy in 2018, and they said the strategy promotes the use of digital representations of systems and components and the use of digital artifacts to design and sustain national defense systems. Tom is here today to help explain all of those words and guide us through the fundamentals of digital engineering and its implications for national defense. Some administrative remarks before we get started. All of the attendee lines are muted. If you have a question during the webinar, you can submit your question in the question box in the webinar panel on the right side of your screen. We will do our best to get through all the questions during the Q&A today. We are recording today's webinar for members unable to attend and for any member who wishes to review the material at a later date. Within the next few days, we'll post the recording, the slides, and the answers to the Q&A to NDIA Connect for your review, as well as our YouTube site. Now I'd like to introduce our speaker, Thomas McDermott. Tom is the Chief Technology Officer of the Systems Engineering Research Center, or SERC, at the Stevens Institute of Technology in Hoboken, New Jersey. With the SERC, he develops new research strategies and is leading research on digital transformation, education, security, and artificial intelligence applications. Tom also teaches system architecture concepts, systems thinking and decision-making, and engineering leadership. He provides executive level consulting as a systems engineering and organizational strategy expert, applying systems approaches to enterprise planning. He's also currently serving on the board of directors of the International Council on Systems Engineering. I know Tom well from his work within the DoD community and now at SERC, and there's no better person to give us this great overview of Digital Engineering 101. With that, I'll turn it over to you. Thank you for your time, Tom, and thank you for this presentation.
Thanks, Arun. So if you're not familiar with the System Engineering Research Center, it's a university-affiliated research center that's sponsored by the Undersecretary of Defense for Research and Engineering. And so we're actually a network of universities that's managed by Stevens Institute of Technology, but includes 24 other universities who all have PhD programs in system engineering, including Naval Postgraduate School and Air Force Institute of Technology, our military partners. And so the work I'll talk about is work that's really going on all across that network, as well as government and industry. So I'm out here at the International Council on Systems Engineering's annual meeting in a hotel in Torrance, California. The magic of digital transformation says that we can do this remotely. So up front, thinking out in the future, imagine if we made our acquisition decisions and our high-level design choices based on looking at models that people produced in synthetic environments. So we were able to fly an airplane in a synthetic environment to understand its performance up front, ideally saving money. And imagine if those models existed through the life cycle, so that any system that we have has this digital twin that's maintained and exchanging data over the life cycle, so we can enable better maintenance and upgrades. And imagine that those models all went into our training system, so that human operators were training to fight in the same models that designs were done in. And then imagine as we develop these libraries of models of different types that, we can run these campaigns of experimentation where all new concepts were developed in these digital environments. And so we're on a journey here. We're probably medium way through that journey. And I'll kind of describe to you where this is and what this concept of a digital engineering is all about. So before we do that, let's take a step back and kind of look at how complex systems have classically been developed and deployed. And so traditionally in this area of systems engineering, we would normally start with a validated need or opportunity or something like that. And then we would go into a process where we functionally model and analyze the system and its performance in order to specify what it should do, and then go into a bunch of different engineering analysis stages, looking at things like security and safety and reliability. And so that's traditionally been somewhat of a linear process. And all of these groups that work together, generally the chief engineer of the program or lead system engineer in the program, they have this human task of trying to communicate across all of these discipline areas and different functions. And so, up till now or a while ago, a lot of that communication has been done in paper documents and PowerPoint slides and these sort of things. And so digital engineering is about getting into a fully digital workflow. If you think about, say, a Navy autonomous drone, for instance, the complexity of the organizational aspects of that are huge. It's a complicated system, very complicated system, but you've got hundreds or thousands of team members working on these types of systems. And this chief engineer, these small group of people, they're expected to understand and manage this whole thing across multiple organizations, including the sponsor for it, as well as all of the contracting activities and subs and all the things that go up into making a complex system like this. And so I didn't throw the slide in here, but many of y'all have probably seen a slide that the next airplane program is going to cost the whole DoD budget. It's the complexity of managing this that's gotten out of hand because these systems have so many parts and so many complex relationships that have to be safe. And so in the engineering discipline, and digital engineering is about the discipline, we're dealing with a historical process where each engineering discipline has its own language. Each organization involved has its own culture and language. Each one of those has its own tool set. And so the analysis and then the decisions that are made have to be integrated together by these superhuman people. And, even if there are people who can do that, there's maybe only a handful of those type of people that can effectively understand all those relationships. And so we need these digital tools to help us out and help us manage the analysis and decision-making process for a highly complicated or complex system like this. So in order to give you kind of an example, let's just look at this unmanned drone, Navy drone, performing in-air refueling autonomously to a military tanker aircraft. And so the particular scenario here is refueling the unmanned aircraft. And all the way down at the bottom of this, there might be a part. That could be the valve, the fuel valve, right? And so we call that a cross-domain object. It's cross-domain, not because it's a valve, but because it lives partly in the mechanical domain. It's a valve, and the electrical domain, it's a cyber-physical system, so you have to open and close the valve. It lives in the operator domain because there's actually a person on the ground that's transmitting messages in order to cause that valve to be managed in different situations. It lives in a communication domain because that control goes over a network. And then it has specialty domains. So it connects to a fire control domain because it has to be connected to a fire control system that'll shut it off if something happens. And it has to be connected to a specialty engineering domain like safety, for instance, so that we can evaluate all this stuff working together in safe fashion. And so, if this machine you're working on is a bicycle, a human pedaled bicycle, that set of relationships, even down to the gear and sprocket, is relatively simple. If it's a in-air refueling valve on a drone that's controlled over a network, that part itself is not necessarily more complicated, but the relationships that are managed around that part become very complex, particularly if each one of these domains is operated on by different organizations. And so the organizational aspect of this becomes quite difficult. So you can kind of see the problem that we're entering into, and it was expressed really well by Modny and Netjes in this paper that wrote about 10 years ago now. It's no longer feasible for us chief engineer type people to fully comprehend everything that's going on in these relationships in these very, very complex systems. And so that's part of the issue. But the main issue that we have is when we launch into designing these systems and we allocate the work down to those teams that are doing valves and control systems and things like that, those engineers have to take their eyes off the big picture, work on their job at hand, and they tend to lose sight of the overall system design that is the product itself. And so what happens, you end up finding errors or anomalies in these interfaces between disciplines. And so we need a better way. And so that better way is effectively digital connectivity of all of these disciplinary tools, and the growth of that in the future. And that's what digital engineering is all about. It's about this kind of refactoring, if you want to call it that, where all of these domains that have their own homegrown parametric type tools that they use, that are not interoperable with each other, that have different languages and different subject matter expertise, can be brought together, not into a single tool, but in an approach to connect them together. And we'll talk about some of the technologies for that. And then it's about a convergence in engineering and management and these other disciplines on the methodologies for using those. So, you know, anytime we have to do a human translation from one domain to another, if we have to jump completely into different domains and tools, then confusion can happen. And it's then about how we collaborate on the inputs and outputs. So, you know, we're able to join each other virtually in a webinar like this. Engineers can then join each other virtually and look into each other's tool sets, and have much more real-time and correct feedback. And then finally, it's about putting that together into our organizational cultures and our training and all these other kind of things where the use of these tools becomes more natural. And so, you know, the tools will help over time create more of a human convergence on how we design and synthesize these rather complicated or complex systems. So that's our opportunity space. And I'd say, you know, we're partway there today. So instead of having that kind of linear type of process, then we get into this process where we can iteratively share this information consistently all around the program at any stage. It doesn't have to be just shared at a major design review where everybody comes together, but we can do this continuously by collaborating together within the model space as opposed to on PowerPoint slides or other things like that. And as the computing power and the bandwidths we use continues to grow, then what you'll see is that we'll scale to more and more of this over time, where we're able to connect more and more types of models together. So we're not going to be all the way there for a while yet. So one of the things that in my community in system engineering that we've been working on is called model-based system engineering. And so what model-based system engineering is actually building in our domain these high-level architecture models and lower-level system models that ideally connect all of these disciplinary components and behaviors together. And that's what we'll want to see as we go through the process. And so the challenge is then in this model-based system engineering role is, what do those types of models look like? So digital engineering is the transformation that will go on as we go through this process. So what's the value of digital engineering? You know, we often see pictures like this. So, you know, we have all of these highly complex different types of models that we might choose to use where we're integrating across aero qualities and cockpit interfaces and things like that. And there may be a misperception out there that the value of digital engineering is bringing all this stuff into one tool or building big giant models. And in the long term, we need to get over that misperception a little bit, because we're not trying to make one model to rule them all or anything like that. It's really an issue of how do we connect the disciplines together. And so after talking to a lot of people and kind of looking at this translation in the work we've been doing, we've kind of taken this point of view, well, maybe we just kind of need a little bit of different mental models of what this is about. And so one of the first ones is best expressed as a cartoon. So if you think about the process of doing an engineering job across disciplinary domains, then what you have today is you have individual humans working with individual tools, and they do their work and they exchange it, usually a lot of manual process, into another tool that another human's operating on. And through that chain of human interaction, then at the system engineering level, they produce an artifact. It could be PowerPoint, it could be a document, it could be a high-level model. And that artifact is what drives our decisions. And so we're not seeing that artifacts change. What we really want to see is that process get connected generally. So each one of these diamonds is a data model in association with a tool. So ideally, when you talk about what's the value of digital engineering, it's connecting all of these data items together. And that data model, that sharing of data, that historical libraries of data and models, those things are the glue that we'll have in these artifacts. So, it's not about, for instance, making things like PowerPoint or documents going away. It's more, you can think of it more as embedding the engineering into these graphical formats to make it easier to drill up and down into the data. So what you might be reviewing in a design might still be a PowerPoint with a graph in it or a piece of three-dimensional CAD model. But if you see an issue, you can tell the engineer, hey, go try looking at making this change. They'll do it and it'll flow straight back up into that artifact. So really what we want digital engineering to do for us is create this connectivity. And the value of digital engineering is a process that's more seamless and efficient. We reduce some of the human manual steps of finding and updating data and models and replace it with automation while still keeping the naturally human steps of doing the changes and evaluating those. And so in a design review sense, you might be able to say, hey, go do this change, come back to me in an hour, whereas it used to be, go do this change, take an action item, and come back to me in 3 or 4 weeks with the updated study. We want to see that become really seamless and efficient. And the challenge that we have is interoperability of data and models. And it starts at the data layer, interoperability of data. And so you can see things like libraries of data and models becoming things that we use or starting to use normally. And they're just connected together in different ways. So if you're thinking about implementing digital engineering, you might get focused on buying Cameo or some other tool like this. What you really need to be focused on is how I can make this process more seamless and efficient by connecting things together. And that's where we want to get to in terms of purpose and value. So moving back from cartoons, in order to understand the technology, let's look at some of the foundational enabling concepts that we're using here. And so the system engineering part of this, we call this descriptive models. And I'll talk through an example of that. And then at the organizational or enterprise level, it's adoption of different modeling methods and methodologies. And then down at the technology level, it's digital transformation. It's relying on things like semantic web technologies to enable interoperability of data, and then building out these digital engineering tool environments and managing environments in order to enable use of those models and data in our analysis. So that allows us then to do multidisciplinary design and analysis and optimization of our designs across disciplines. And the output of that, what we ought to be measuring, is automation in the data discovery and automation in the model checking processes. And the key measures of this are what we call cross-domain traceability and completeness. So can we actually show in the tools that we haven't missed something? We don't have a gap in our design, and let the tools find that for us. And then in the process area, it's then, can we push the finding of those anomalies, gaps, and other things much earlier in the design process, where we're operating in the model world instead of after we cut metal in the physical world. And so in terms of technology enablers, this is where the technology is going to go. So if you're not familiar with model-based system engineering is generally the process of developing these higher level descriptive models that describe the system as a whole, as opposed to the detailed models of the mechanical, electrical, and other disciplinary functions. And so it's a whole lot like Mylar drawings to computer-aided design in the mechanical space. But when you think of systems being mechanical, electrical, human, software, all those other things, these descriptive models help us to tie it all together. And so without going through all the details on that, you can think of the system model is this unique work activity that we want our system engineers to go do, that is effectively the description of how all these models and disciplinary engineering activities connect together. So this idea of a system model becomes a value-added activity because it's pointing to the current configuration managed latest version of all that engineering in a modeling environment where it can be automatically updated and connected as the design develops over time. And so the system model is kind of this unique entity. So I'll spend a little bit of time on this. If you haven't really ever seen system modeling in action, this is just sort of a graphical description of how a system model gets developed and used. So I'm usually starting with high-level user needs or requirements or opportunities, which is truthfully quite a human process of understanding what the stakeholder needs are. And so I'm taking those into requirements and use cases and functions. And so I'm kind of always starting with, all right, how do I describe the system that would satisfy that as a set of human-machine interactions, which we call a use case model, a set of activities to be performed, which we call an activity diagram, or behaviors to be exhibited. Some people call these capabilities. And in those capabilities and use cases, what are those key requirements that I need to maintain to satisfy the end user? And so we have 3 different modeling types at the system level that we use: this use case, activities, and requirements. And that's kind of the start of it. And we move from there into what's known as a structural diagram, a block definition diagram in SysML language, where we allocate that down to pieces and components. And so that valve in that refueling system is a component of the system. The operation of opening and closing that valve is an activity, and the human ground operator's interaction with the system to move in and manage that is a use case. And things like interacting with fire control or interacting with safety, those become things that we would define in requirements. And so all that stuff comes together and gets connected together in this modeling environment. And we're not done there. So once we have that allocated out, then we can start formally controlling the relationships between all of those components and activities as interface diagrams. We call that an internal block diagram. And so that allows us to bring some control or configuration management to this process. And then we can take that back into the high-level ConOps, and we can link all of these parts and all these use cases and all these activities together into what's known as a scenario diagram or a sequence diagram, where now we can actually go back and say, here's the end-to-end performance of the system. And that's captured in this modeling environment. And we can continue on from there when we have that to then start saying, all right, well, if I drill back down into this actual activity of opening and closing a valve, that control system activity also can be captured and specified, and that's known as a state diagram. So the system engineering is using all those tools before they even get to the point perhaps where they're trying to define the engineering performance, the mathematics, if you want to call it that, in a parametric diagram. So we can capture all this stuff into a systems diagram, connect everything together, and then use it first to actually build the model of how we're going to test all this stuff. So we can build modeling of our test activities and connect those in. And then after that, to build models of our engineering analysis. So we can take those and go into different other tools to do things like multi-physics analysis or safety analysis in an Iliades type tree or any of these kind of more disciplinary models. So if I'm designing a new version of a bicycle that gets pedaled by a human, I might just be interested in the structural and interface components at the block level and the performance at the engineering level, and I might not be interested at all in some of these other behavioral models that the system has to operate in. So if your business is building bicycles, you know, you might not be implementing all of this system level modeling. You may just need to use certain components of it to provide configuration management and reuse of different parts in your engineering system. But if I'm doing an autonomous UAV that has to go into an automated and air refueling activity, then all of these behaviors have to be captured too, and our models have to get a lot more, they have to cover a lot more ground, if you want to call it. So in a systems modeling tool like SysML, we have the opportunity to describe all this stuff, but not just describe it, to actually link everything together. And we link all those things together in order to feed that down to lower and lower requirements at the part level, and then ideally to trace it all together. And so in the end, the system modeling tools will automate this type of traceability so that we'll know if we forgot something in all this design process, that'll pop up as a gap. And so you can kind of see this whole flow. So this is kind of a mature process now, although, you know, the use in organizations and the enterprise use of it is a little bit less mature. But that's what we're trying to get to. So you think of this modeling activity, it has to be done because it adds value, and that value added is actually controlling all of the configurations of all the parts in a complex system over the full life cycle. And that's what we mean when we talk about model-based system engineering within a digital engineering environment. So we can then take that in model methods at the enterprise level, and we can drill down. So you might envision in that UAV that the government has an operational set of models, mission level simulations that they run to understand the performance they want. They have a set of user capability models that describe those use cases to manage a thing. And the government might build their system model that tells a contractor, hey, this is the top level architecture of what we want you to design. And that would be your RFP. Your RFP would then go to a contractor, and they would feed back their final system model, which over time then allocates down to all of those subsystems and components in their full supply chain. And so all of these things get linked together and they get shared. And so the efficiency comes from eliminating the manual human trade-offs and paper trade-offs across all of these different model types. So the acquirer and the developer, they can get together at any level in any one system, and they can share what they have. And so we've demonstrated in programs that we can do this 100% digitally, all the way down to signing off on a drawing or signing off on a specification in the digital tools with no what you might call human trade of paper. Everybody's working together in the modeling set. So we know that we have the technology to do this today, and a lot of the development from here on out becomes how organizations use this stuff to do their enterprise level management of their systems, as well as how they do it to sponsor reuse across capabilities. So we have these modeling tools, and then we have these modeling methods, and then we want to get to the point where we can do reuse and interoperability. And this is where the data comes in. And so a lot of the magic that's going to evolve over time actually comes from the World Wide Web and semantic web technologies. So one thing that you probably can understand is when we talk about system level modeling, and we talk about describing things, those have been quite highly what you might call a language-based model. A requirement statement is a piece of language. So it's a semantic model that's at a high level that describes a meta model for how things connect together. And so as this evolves, the tools are going to take advantage of these World Wide Web type technologies and artificial intelligence and anything else. We'll be able to use that to gradually over time build out all of this checking and consistency in these relationships. And so it means doing upfront work to capture things with common language or ontology, build the meta models that constrain it. We call these reference architectures, and then apply the tools, and over time redevelop the tools so they operate with data. And what you want to get to is sharing of data underneath. So pretty much all this future is going to evolve the same way you see things like Google and Amazon and all these other people evolve. And in fact, those companies are driving a lot of the technology underlying this today. So that's a core technology to watch, how these things evolve over time. And in the SysML language space, the version 2 of SysML that's coming out shortly has really been redesigned fundamentally to take advantage of these semantic web type ontologies. What we really want to get to in the end is driving ourselves off of reuse and data and models. And so this kind of traditional V diagram of system engineering, where you start at the concept level, go down into design and come back into test. It's not that that's invalid, but what we want our habits to be is the evolution of the ability to jump into this process at any point with our collections of historical data and models. And so we can view this process not as a V anymore, but as a circle with data at the center, models as the representation of the data into these views, like I showed you in that buildup chart, that feed our digital artifacts. And the human process of that then becomes the transformation of data into views that I can analyze and make decisions around. And so the challenge that we're seeing in our environment right now isn't so much the digital environments, but it's how we get the engineering processes to be more highly data driven. And so ideally this will help us over time. And if you look in terms of performance, where you're really starting to see the benefits that show up. So for example, the T7 trainer program, it's been reuse of data and models that have really improved the speed with which we can go from top level design to actual having parts on the other side. So reuse is kind of the key term. Probably where we're sitting right now in terms of organizational adoption is what do these giant digital engineering environments look like? And so I won't do anything more here than kind of give you a view of a complexity of what you might look at as a full digital engineering environment. This is a MITRE picture, but it can be a complex set of tools that have to be put together. So just quickly, where are we? We did a survey. This was back in early 2020. And what we were trying to do is understand where people were in terms of their maturity. And so we used what Cozy calls their digital engineering maturity matrix to do the survey. And so you can imagine asking a question like, my modeling provides measurable improvements in my process. Do you agree or disagree with that? And so you can see where we were in the state. You know, a lot of disagreement. A lot of people don't consider themselves to be very mature yet, outside of a few small areas. And so I think this is improving over time, but we're in the earlier stages of what's going to be a multi-year process of evolving our digital engineering capabilities. Looking particularly at what's the benefit, measurable improvements of modeling versus can I measure it? You can see nobody knows how to measure it yet. And so we've been focusing on that. So this has been an interesting study, but our student looked at 847 papers that mentioned model-based system engineering, 360 of which pointed to the benefits. And out of that, there were only 2 of them that actually had measured the gain itself. All the rest were perceived. And so, you know, there's a lot of perceived benefits today of model-based system engineering and digital engineering, but not that much lessons learned in terms of, oh, I actually save this much money. So even though managers want you to state return on investment, we've got some development to go to get there. We also looked at adoption. I won't go through the details of this, but the adoption model for this, it's like any digital transformation, it's fairly complex, and we need to trade lessons learned between programs. And finally, we took all of that into what do I measure? And so we actually released as a community mid last year the first digital engineering measurement framework through the Practical Software and System Measurement website. So we're getting to the point now where this can be a practice that's measurable and be adopted over time. So how long is it going to be before we get back to that first slide? You know, I think I look back at the evolution of computer-aided design into these complex systems. It took 30, 35 years to get as mature as we are today. It's going to be a continuing process that's going to span a number of different years. In the DoD, then, the strategy, which was released in 2017, so if we're 5 years into this strategy, you know, we've got a long way to go, but the momentum's building. And so we're starting to see more and more programs and organizations adopt this, and hopefully we'll accelerate into the future. So I'll stop there and leave the rest of the time for questions. Hopefully I gave you some view of what we're talking about technology-wise when we're talking about digital engineering.
So Tom, thanks for that great presentation. We have questions coming in. I encourage the audience to send in more questions by the app. Let me just start going through some of these questions. What is, based on this DoD rollout, what do you think is the most impactful use so far of digital engineering in a DoD program or system that you've seen?
So one of the programs we worked when I was at Georgia Tech was the Air Force Distributed Common Ground System, which is a really complex network of platforms and intelligence consoles. And so the government had sort of lost configuration control of that, and it had grown hugely complex and unmaintainable. And so we used digital engineering to recapture the baseline and then control all the upgrades to it in the future. And that building out of that systems model became the thing that everybody could work towards. And so, you know, I think we're seeing it in the already built systems advance at the front end. Now we're seeing programs that are going fully into it. So like the Navy's Columbia submarine, the recently announced Army FLRAA helicopter, those things are actually showing, you know, how we can contractually exchange the models. So we're seeing these impacts, I would say, evolve at the lower levels. We're not seeing the idea that we've gone completely digital with everything happen in very many programs yet.
Okay, I'm going to be merging some questions here because there's so many coming in. In terms of it seems like this is all going to be run on fuel, which is data. And so talk about the state of DoD's ability to share data appropriately to make use of this capability. And then touch on also the issues of proprietary data and even classified control data.
Yeah, so I would say in the 5 years since the strategy was released, we've done a lot of work on sharing models, but sharing data remains a problem. And so in terms of our research in the CERC, we've sort of moved off to, well, if the common ground is the underlying data, how do we do better at sharing that? And all of the traditional issues with the government sharing of data that include proprietary issues and security levels and all those things apply. So, we're working through those processes, and I don't have the answer for you. The answer we're working is, hey, give me your lessons learned and let's share them with the community. I think at the contractor level, as they figure this out, their secret sauce is a competitive advantage of how to manage this data. So, we need to see that evolve. On the government side, of course, the government's fault is behind them in terms of building out these data sharing processes, but they're working hard on it. So, it takes sort of a cultural revamp of how we do things. So that's why we think it's going to be a fairly long-term thing, but I think the community understands that we have to do this. We can't have a threat data set that's delivered as an appendix, a Volt document into a contract anymore. We actually need the parametric data that underlies those threat characterizations to be available to the developer at the right classification level so they can directly import it into their models. So a lot of this is being supported by the move of the government into their own cloud environments so that they can manage at a top secret level these type of models in their clouds. But then how the government and contractor then share data across the contractor and government clouds and who works in which systems is something where I would say we're just starting to figure that out quite a bit. So I don't have any magical solution yet. It's a significant cultural change that has to happen over time.
That's fair. Okay. So the one question here is how can digital engineering be leveraged in a time-sensitive, budget-constrained environment? I mean, the presentation sort of you take away that, well, it's going to be used good for systems of systems and large systems, but is it good at the other end of the spectrum as well for more rapid, maybe smaller systems that need to be done maybe at lower cost?
Yeah, and so I think you see it happening already. So you take like my bicycle example, right? How can a bicycle company get directly from design to manufacturing in a much simpler environment? Well, they do that with CAD models, right? The CAD/product line manufacturing systems are really pretty mature in terms of doing a simple system. And then in that case, the system model, you're really just wanting the system model to manage, for instance, your supply chain, your parts, and related interfaces. So it's all about being able to reuse. And so we're seeing a lot of the maturity happen in the ability to reuse electromechanical stuff. We're seeing less today in the ability to reuse software and complex software hardware interactions. And so that's an area where we have to evolve quite a bit. But I wouldn't recommend that an organization go into a major digital engineering full system modeling environment unless they're dealing with systems that are of that level of complexity. Just to add a comment, I would say we're seeing probably the uptake happen more in the automotive industry right now. And there may be medium scale complexity compared to some of what DoD deals with. But what they're finding in their environment is in order to manage this evolution to automation, self-driving cars in conjunction with all the other things that cars have always done, this investment in system modeling is allowing them to reuse these capabilities from model type to model type. And so when I look at things like who's measuring digital engineering right now, we're learning from the automotive industry actually quite a bit about how to really do these things right now.
So that's a nice feed into this next question. There's a set of questions that seem to be around the idea of the models are very nice, but what happens when they meet the real world? So one of these questions is, can you speak to the need for accurate models on the manufacturing side, where real world parts aren't exactly what you thought, supplies may not be exactly what you thought. So that's one example of the real world maybe confounding the models. Another would be the human factors element. And how do you handle the human factors piece of it? Well, it's very nice and it fits the soldier, but it's too heavy for him, that sort of thing. And then one other sort of real world thing is some systems are really complex, like microelectronics. And so are the models in any position that they can handle really complex systems like microelectronics? So sorry, I was a bunch there.
Yeah, and so again, I would caution you to not think like a model of a semiconductor chip is anything like a system model of the computing system that will use that. It makes no sense to try and build a modeling tool that will do both of those things. They're too specialized, right? It's all about how do you connect the data together so one model is informing the other. And that connectivity has to be driven by what types of decisions you have to make, right? That should drive your modeling strategy. And so we look at things like manufacturing lines. I mean, Tesla's been a great example in the automotive world where, they can make design changes into the physical components of their car in days, and they can export those to their manufacturing line, and they can retool their machines out on the manufacturing line fully digitally in a matter of days or weeks, as opposed to months or years in some other cases. And so, I think Elon Musk once said, it's not the fact that we're so agile, it's the fact that we're so digital is what makes us have the ability to do those kind of things. And so the idea of a digital twin, you take all these models of information and then they feed directly into your training system, into your manufacturing system. When you get to this idea of a digital twin, then you actually connect the real world to the models. So the real world data then feeds back into the models so that you can roll out incremental improvements over time. And so the difference between a digital modeling environment and a digital twin environment is that connectivity, that digital connectivity back to the real world. So you're collecting real world data into your models. I'm not sure I answered all those questions, but
No,
hopefully I got some of them.
Let me poke at that based on another question here.
Uh-huh.
Do you run the risk of constantly perfecting the model while delaying the build based on some of that real world field feedback you're talking about, and you never get to the physical asset? So as opposed to building an 80% solution, going through DOD style OT&E processes, etc.
Yes, I did. Obviously, that's the human problem with this, right? Is what's a good enough model? It's the same thing as what's a good enough part, right? How far do you want to go? So your enterprise processes, again, you have to think of digital engineering as being that infrastructure that connects all of these disciplines and models together. Your process for using them has to be intentionally developed into a methodology. So yeah, I mean, I think I've seen examples. Well, I've lived through examples where the engineers who are system level modeling have to figure out with the engineers who are domain level modeling, what's the right information exchange? How much should we define for you and what's helpful? And that's, I think, a lot of our lessons learned. So, if you can, for instance, make the interfaces that they're working to very clear, or the end-to-end functional scenario that they're working to very clear in your models, then you put them 50% farther along in their designs. And so each one of those relationships between the system modeler and the disciplinary modelers, those are things that we're going to learn and evolve over time.
So there's a set of how do you start questions. So try to answer that from a different perspectives. There's the how do you start question from a, let's say, a government DoD perspective. How do you build the enterprise, the connective tissue you were talking about? for different users, both in government and industry, to start? And then I'll ask you from different perspectives. Start with how do you start from a government perspective?
Yeah, so we did a workshop 2 Decembers ago with exactly that question: digital engineering, where do we start? And so, one of the key things is, what are your assets? Who owns the models and who owns the data? What can you start connecting together? And so that appears to be one of the fundamental questions that's difficult to answer is, who's in control, right? Who's the authoritative source for those data and models, and how does it get transitioned? From there, it's building up the tool suites. And so, we need to understand a whole lot more by sharing lessons learned about what is an effective tool pattern that you might use to develop this type of system versus that type of system. And, there's been a lot of, we bought Cameo and we built a system model and we're done. And it's not anything like that. It's actually a much more complex tool space to realize those efficiencies. And so, that's, I think, probably one of the biggest barriers we have in the government right now is sharing lessons learned and information about how to do this. The other issue that we're having, and we're doing a big session out here in California on this on tomorrow, is workforce. So it's not, what's the training, what are the roles, who needs to look at what, but also, right now in industry, good system modelers are being poached like good AI people. So there's not enough of them, and there's a tremendous competition for this workforce that's out there. So, we have a lot of these same issues in any large cultural change that we have to work on. And obviously on a salary basis, it's going to be difficult for the government to compete with industry and for expert modelers, if you want to call them that. So yeah, so going back, when you look at the slides to look at that little adoption model that I showed, that will give you a clue on some of the things you need to do to start, because it is an enterprise level transformation.
Let me say the other end of the spectrum of the where do we start question. If you're a small business, sub-tier supplier, working on semi-complex parts, how do you approach this? Do you buy a service? Do you buy a software package? Do you look to hire a grad student with a degree in digital engineering? What do you do?
Yeah, so I will say, when we talk about system modeling, the tools are rather expensive. And so arriving at your data exchange format is step number one. So if you're responsible for the valve, right, that's, a digital data sheet is effectively what the program needs from you, maybe material characteristics and all that kind of stuff. So I wouldn't invest in this stuff at all. If you're the electromechanical valve management system, subsystem, then you've got a balance, right, of how much system level modeling, how much tool investment do I need to do that, or is something that we can just do in electromechanical CAD. If I'm a lead system integrator, obviously it's very important that I invest in these things. And so then you get to companies, and we've worked with some of them who, they might provide radio systems or ground stations or things like that. They're the ones that are going to have to do this learning and evolution of, how do I build up my system level digital engineering capabilities versus the lower level engineering, which is already fairly mature. And truthfully, it's $2-3 million to do an basic enterprise transformation around system modeling right now. It's not cheap. And so we have to watch that evolution over time too.
All right, I'm going to try to cram in 2 more questions before we close here. One is, can you clarify the difference between digital engineering and digital transformation?
So the digital transformation is this underlying data interoperability, right? It's the same problem that we're all having everywhere with digital transformation. Do I have the data? How can I get to the data? How do I use it to make my processes run more efficiently? And so in the engineering community, that word data and data management is sort of new to us. in engineering. In engineering, it was, how do I use this tool? Well, the problem we have is your disciplinary tools don't necessarily connect to other people's disciplinary tools. And so we got to get to the underlying data. So that's really when we talk about digital transformation, it's this idea of data driven, and that's the shift that's just starting to be made. When we talk about digital engineering, then it's all those other, how do you connect together all those other disciplinary tools, which honestly they've been used for 30, 40 years now. I mean, we were doing fully digital airplanes when I worked on F-22 and in the 1990s. It's not necessarily new.
So, and then the last one I'll say is, I'll ask is, at some point, does the complexity of the subsystem overwhelm the models and overwhelm the ability for useful exchange of information between the models? This case that's cited in the question is the complexity of the microelectronics embedded within a complex defense system.
Yeah, and so the real challenge here is, can you have a good system modeler that understands the level of abstraction that your models need to be at to make the right decisions? Because obviously, I'm not going to capture the details of an electronic chip into a high-level architecture model. I want to show the connectivity, but I want to show the connectivity in the decision space that needs to be made. So, this is where the art comes into play, and where there's talent shortfalls. I mean, a good modeler, a person that understands how to build models and what they're used for and how to use them to bring value to the disciplines, is worth their weight in gold in this process. So yeah, again, we have to get out of this mode that we're going to put everything into one tool. It's just never going to happen, that I can tell. It's really, we got to focus on the connectivity.
Well, thanks very much for your great presentation, Tom. You can tell by the questions people were really interested. So I really appreciate you doing this, and thank you to all of the attendees for joining us today. We will post the recording online as soon as possible. If you have feedback about the Tech 101 series, especially topics you'd like to see us cover in the future, please email us at eti@ndia.org. I also want to take the opportunity here to highlight some upcoming ETI events. There will be our next 101 presentation will be Systems Engineering 101 on February 23rd at 1 p.m. with Jim Feist, sponsored by AI Tech. We really appreciate their sponsorship. ETI is also proud to announce that we're having our first annual Emerging Technologies Conference, August 28th to 30th this year in Washington, D.C. at the JW Marriott. Registration information will be on our website, or reach out for more information about that. We're looking for thoughts and suggestions on what people would like to see in the conference, and opportunities to participate in the conference. With that, I will close the session and thank everyone again for attending.